Okay, so thanks for the opportunity to speak. So today I'll be talking about some joint work with Genevieve Walsh. So let me start by stating the motivating question and telling you the main result. Okay, so the motivating question comes from a pair of conjectures of Wall and Borel. So this conjecture is sort of a basic existence and uniqueness question for aspherical manifolds. So it says, so the existence part is that for every G, which is finitely presented Poincare duality group of dimension n, there exists some M, which is a closed topological aspherical manifold with fundamental group G. And then the uniqueness is that any two such M and M prime with the same fundamental group are isomorphic, or are homeomorphic. So let me state I want to state a relative version of this conjecture because it'll be relevant for the talk. So the relative version is if you have a pair, GP, where P is a subgroup of G, and if this is a PDN pair, which I'll define in a second, then there exists a pair of closed, or a pair of aspherical manifolds, aspherical M and N with, so M is a manifold with boundary N, and well, these have the right fundamental group. So pi 1 of M is G and pi 1 of N is P. Okay, so we saw the definition of PDN groups yesterday. Let me remind you of it now and tell you what a PDN pair is. So for a type FP group G, we say that G is a PDN group if the cohomology of the group with group ring coefficients agrees with the reduced cohomology of the sphere of dimension n. And for a pair of groups, GP is a PDN pair if so one way to say it is, so if P is a PDN-1 group, and the group theoretic double, which I'll denote G delta, so this is the amalgamated free product, G with itself over P, if this group is a PDN group. So it's perhaps more proper to call this a theorem. So there's a different way you could define a PDN pair, which looks closer to something about the cohomology of the group. And then Bieri and Ekman show that this is equivalent to what I've written here. Okay, so and the basic example is if M is aspherical, closed aspherical, and G is its fundamental group, then G is a PDN group. So you can see that easily because the group cohomology with group ring coefficients can be computed from the cohomology of the universal cover of M. And then by Poincare duality for manifolds, this is the same as the homology. So this is compactly supported cohomology, and that's the same as homology with a degree shift. And M is aspherical, so the universal cover is contractible, and, well, that says that you have the right cohomology. Okay. Okay. So yesterday in Jonathan Hillman's talk, we heard about how this general question of showing that a PDN group is the fundamental group of an aspherical manifold is a difficult question, in particular in dimension 3. So I want to tell you about some success for this conjecture, in particular for hyperbolic groups. So the first result I want to mention is the theorem of Bestvina-Mess. Which gives, in the case when G is hyperbolic, it gives a geometric group theoretic characterization of PDN groups. So G is PDN if and only if the cohomology of the boundary of G agrees with the cohomology of the n-1 sphere. And so technically you have to work with reduced check cohomology of the boundary. But okay, so this is the first result I want to mention. Right, so in particular, for example, hyperbolic groups whose boundary is a sphere are PDN groups, and so you expect those to be closed aspherical manifold groups, and indeed that's true by a theorem of Bartels, Luke, and Weinberger. So they showed if G is torsion-free and hyperbolic with visual boundary an n-1 sphere, then G is the fundamental group of closed aspherical n-manifold. And in fact, it's unique. So this verifies the Wall and Borel conjectures in this case.
Excuse me, is that
yes.
enlarged?
Oh yeah, right. Thanks. So there's a huge caveat. So this is open in the case n is equal to 3, and so you need n to be at least 6. Okay. So a few years ago with Jean Lafont, so we proved a relative version of this statement. So again, G is torsion-free hyperbolic. And if in the case when the boundary of G is an n minus 2 dimensional Sierpinski space so this means it's obtained from the n minus 1 sphere by removing a countable collection of open disks. So di are open embedded disks with dense union and disjoint closures. And diameter going to 0. So this is, so a one-dimensional Sierpinski space is just the usual Sierpinski carpet. So if G has this boundary, then we show that this group G is the fundamental group of some aspherical manifold W of dimension n with a spherical boundary. And again, it's unique. Okay. Okay, so one thing one would like is a version of these results for, not for hyperbolic groups, but for relatively hyperbolic groups. So hyperbolic groups with Sierpinski boundary, these arise as, well, one way these arise is as fundamental groups of, say, closed or hyperbolic manifolds with totally geodesic boundary. And so if you replace the boundary, totally geodesic boundary by a hyperbolic manifold with a cusp, then you get a group which is not hyperbolic, but which is relatively hyperbolic. And so you might hope to have a result for those type of groups. So with Genevieve, so we, well, so what we've done is give a relative version of the Bestvina-Mess theorem, at least in low dimensions. So, so the statement is if GP is relatively hyperbolic, which I'll define in a minute, and then the boundary, the Bowditch boundary of this pair is homeomorphic to S2 if and only if this group pair is a PD3 pair. Okay. Are there any questions at this point? Okay, so next I want to, well, introduce a little bit of terminology, tell you what relatively hyperbolic groups are and what their boundary is. And the main point I want to get across in this section is, so there's the typical boundary people speak of when they talk about relatively hyperbolic groups is the so-called Bowditch boundary. And the main thing I want to explain is that the Bowditch boundary for this question of studying the duality properties of the group is not the right boundary to consider, and instead one should look at a boundary defined by Domani. Okay. So let's start with G. So G will be a finitely generated torsion-free group. So we say G is relatively hyperbolic relative to a collection of subgroups if there exists X, which is a proper hyperbolic metric space on which G acts in a nice way, properly discontinuously, and by isometries. And so that if you look at a point on the boundary of X, every point on the boundary of X is either a so-called conical limit point or a bounded parabolic point. So bounded parabolic point means that, well, the stabilizer of Z, which is a subgroup of G, so this will act on the complement of this point. And we say Z is a bounded parabolic point if this action is properly discontinuous and co-compact. Okay, then there's one more part of the definition, which is this collection P. So P should be the collection of maximal parabolic subgroups. And for the examples, I'm going to be thinking about when the boundary is just the two-sphere, the boundary of X is just the two-sphere. This is the same as P being the collection of stabilizers of bounded parabolic points. Okay, so this is the definition of a relatively hyperbolic group. This is a definition. And then in this case, one defines the boundary of this group pair to be the boundary of the space X. And this is often called the Bowditch boundary. So for example, so an example would be G, the fundamental group of a hyperbolic knot complement. So let's say S3 minus K, where K is the figure 8 knot. And then P is, so this is a hyperbolic 3-manifold with a cusp, and for P, the collection of conjugates of the cusp group so here that's just the Z squared subgroup. Right, so this pair is relatively hyperbolic. Right, so a picture, this G acts on hyperbolic 3 space, and the cusp corresponds to these Horrorballs, a collection of Horrorballs. And well, okay, right, so this z squared, this is the Hor ball is a copy of R2, and z squared is acting co-compactly on that, and which is the same thing as saying it acts co-compactly on the complement of point on the boundary. Okay. So there's an important distinction between the case when P is empty and when P is non-empty. So if P is empty, which is to say that G is hyperbolic, then this boundary, the boundary of G, is a so-called Z boundary of G. So I'll define this in a second. But in the case when P is not empty, so that you have some non-trivial peripheral subgroups, then, well, this is not the case. So this Bowditch boundary is not necessarily a Z boundary of G. Right, so let me just say briefly what a Z boundary is. I don't want to focus on this, but just since this is sort of an important point. So this is a definition of Bestvina. So we say that Z is a Z boundary of G if, well, so there exists a pair, let's say X bar Z, so actually, right, before I give the definition, actually I want to just give the example first, because the definition is a little bit technical and abstract. So the main example is when G is hyperbolic, then you can take X bar to be the union, so a Rips complex for G together with the Gromov boundary of G. So this is some simplicial finite dimensional model for EG. Which has this nice compactification by the boundary. And so the notion of Z boundary is an abstraction of this. So X bar Z is a pair such that, so first of all, well, X bar is a compact Euclidean retract, and Z inside X bar is a Z set. And G acts on the complement of Z properly discontinuously and co-compact. And there's one other condition, which is that if K is a compact subset of X bar minus Z, then the orbit of K under G is a null family of subsets. Okay, so right, so maybe one remark. So in the case when okay, maybe let me save the remark. So if you haven't seen this definition before, don't worry about it. So the main thing that makes these Z boundaries nice is that if you have a Z boundary, then it captures well, the duality properties of the group. So another way to restate the theorem of Bestvina-Mess that I said before is that if Z is a Z boundary of G, then you can compute the group cohomology with group ring coefficients by computing the reduced check cohomology of the boundary. I think there should be a shift in dimension here. Or maybe it goes this way. Okay. Right. And so for relatively hyperbolic groups, so Damani showed that if GP is relatively hyperbolic, and so if each of the peripheral subgroups admits a Z boundary, then G also admits a Z boundary. And so this boundary I'll denote like this and call it the Damani boundary. Okay, so let me return to this figure 8 knot complement example. So in this case, well, hyperbolic space with its boundary doesn't serve as a good space to choose for this X bar Z because, well, the action of G on hyperbolic space is not co-compact. Right, so it's not evident that the Bowditch boundary is a Z boundary, and in fact it's not in this case. So the Bowditch boundary is homomorphic to S2, and inside this boundary you have a collection of the bounded parabolic points, which is this dense collection of points. And so roughly the way you get the Damani boundary is to replace each bounded parabolic point with its Z boundary. So roughly the Damani boundary is obtained by replacing a bounded parabolic point corresponding to a parabolic P with the corresponding with a Z boundary for P. So in this case, what you get, the Damani boundary of this pair is a Sierpinski carpet. So you blow up each one of these bounded parabolic points and you're left with Sierpinski carpet. Okay, so now let me give a more precise definition of this Damani boundary. So for a relatively hyperbolic group, well, so let's let gamma be the Cayley graph with respect to some generating set. So you can form the so-called coned-off Cayley graph. Which will be a hyperbolic graph. So the way you get it, so you start with the Cayley graph, and then inside here you see, well, these subgroups. So let's say P1 through PD are conjugacy representatives of the subgroups in P. So you see each of these subgroups in the graph, and then you add a vertex for each one of these subgroups, and you cone it off. And then you do the same thing for each of the G translates of these subgroups. So for each left coset, you have a copy. So you have like GP1 and GP2, and you do the same thing. Okay, so if G is relatively hyperbolic, then this will be a hyperbolic graph. And so one way to define the Bowditch boundary is that from this perspective, is the Bowditch boundary is, so this is gamma hat now that I've added these cone points. The Bowditch boundary is the visual boundary of gamma hat together with all of these peripheral points. So you add a point for every peripheral subgroup. And then the Damani boundary is defined similarly. Where instead of a point, you add the boundary of the peripheral subgroup. Okay, and well, so you have to Damani puts a topology on this, which maybe I'll say something about a little later. But one thing to observe immediately is, well, so there's an obvious surjection from the Damani boundary to the Bowditch boundary. So I'm going to call this map C. And well, with respect to the topologies on these things, this map is continuous. Okay, are there any questions?
So the boundary of P is a circle.
Right. So in yes, I'm going to say that in a second. Yeah. So the next. Right, so in this example, the peripheral subgroups are all Z squared, and so the boundary of each of those is just a circle. But in general, the peripheral subgroups don't necessarily have to have a boundary, and so, well, I don't think you can always define this Damani boundary. And the peripheral subgroups might be something other than things with boundary S1. Okay. Okay, so now I want to discuss something about the proof of this theorem. So the main thing to understand is, well, the difference between the Damani boundary and the Bowditch boundary. So in the theorem, you're given a manifold with Bowditch boundary S2, and you'd like to understand what the de Monty boundary is, since that's the boundary that carries the duality properties. Okay, so the main theorem we prove is that in the case when the Bowditch boundary is a two-sphere, then the de Monty boundary is a Sierpinski carpet. Okay, so of course this was true in this special example, this example coming from this geometric, from a manifold, but in general the same thing is true. Okay. Okay, so first a remark. So this is the main technical theorem that we use to prove this theorem. So I wanted to say just a little bit about the proof. I'm not going to prove it, but so a remark on the proof. So the first remark is sort of an easy one. So knowing that the Bowditch boundary is S2 implies that all of the peripheral subgroups are surface groups. So we know that the peripheral subgroups act on the complement of a point if your Bowditch boundary is S2, then this is just R2, and this action is geometric. And so you can easily deduce from this that, well, P is a closed surface group. It might be Z squared, or it might be a homogeneous surface group. But in either case, P has a unique Z boundary, which is the circle. So in particular, in this case, there is a de Monty boundary. So the situation one has is, so you have this de Monty boundary, which you'd like to understand, and it surjects onto the Bowditch boundary, which is a two-sphere. And you know that, so one thing you know is that this map, let's call it C, is a homeomorphism away from the set of bounded periodic points. Because, well, away from bounded periodic points and their pre-image, this is, I mean, these sets are equal. And the topologies agree. And then you know that the inverse image of the collection of bounded periodic points is a dense collection of circles. And of course, the Sierpinski carpet has the property that, well, it has a map to S2, which is a homeomorphism away from a countable collection of points, and on that countable collection of dense points, the pre-image is a circle. But so one thing, well, but there are a lot of other spaces which have that property. So So let me just say, one thing you have to rule out is maybe something like the following situation, where the Damani boundary, rule out that the Damani boundary might be something like something like this. So it's going to be a complement of a union of disks in S2, but it's not going to be a Sierpinski carpet because the diameter of the disks isn't going to go to 0. So let me draw it something like this. So you have these, I'm removing these disks which are have diameter bounded above, and maybe they're converging to one of these other disks that I removed. And then there are some other, so this is supposed to be a dense collection of disks, so you add some other disks. You know the group G is going to act on this thing, so, well, I guess you know that you'll have to see this pattern sort of equivariantly. But okay, so in fact, there's an old theorem of Moore that says, well, if you have a countable collection of dense disks in S2, which, well, so let me just say it in words, which define an upper semi-continuous decomposition of the two-sphere, then if you collapse all of those disks to points, you'll get the two-sphere. Okay, and there's lots of examples of spaces like that that aren't Sierpinski carpets, and so you have to somehow rule out that the space that you're getting isn't one of these weirder examples. Okay. Okay, so I'd like to give you some indication of why you actually get a Sierpinski carpet and not something else. And for that, I want to say just a word about the topology on the Damani boundary. Right. So the main thing to understand is, for this theorem, is the topology on the Damani boundary. And well, okay. So let me say something about that. So let me start with the Bowditch boundary. So I'm going to give you a basis for the topology, and this will shed some light on what sort of space is appearing here. So let's suppose we're, well, given some bounded parabolic point in the Bowditch boundary, and a finite subset of the corresponding peripheral subgroup. So then there are open sets which are defined as, so those points in the boundary for which there exists a geodesic from this bounded parabolic point to x that avoids the set A. So let me draw a picture. So you have inside the coned-off Cayley graph, you have your peripheral subgroup P, and this cone point. And if you pick some finite subset maybe set this to be A, and look at all geodesics starting at this point, whose first vertex doesn't land in A. So another way to draw this picture is if you think about this cone point as, well, so in the boundary of the space X that the group G acts on, and you pick a horosphere, then if you pick some maybe compact subset A of the horosphere and look at all of those geodesics which emanate from this bounded parabolic point but don't pass through here. So you have like something like this, and you see that this gives you a neighborhood of this point in the boundary, like this. Okay, and then by increasing the size of this A, you can get a neighborhood basis. Okay, and then in the Damani boundary, so suppose we have some Z, which is in the boundary of some peripheral subgroup, and V, which is a neighborhood of Z in P together with the boundary. And let me set A to be the complement of V in P. So then there's a basis of open sets which are of the form V intersect the boundary together with all of the endpoints of geodesics which emanate from this base point and avoid A. So this is a subset of the Bowditch boundary, and then you look at the pre-image in the Damani boundary. So, so now another picture. I'm going to draw the peripheral subgroup now as something sort of two-dimensional. So if I have some point Z like this, and I pick some neighborhood of it, V, and then A is the complement, so now A is some infinite set, and I'm looking at all of those points, geodesics starting from the base point, which avoid this A. So sort of picking okay. So that's the open set. This gives you a basis for the topology on the Damani boundary. And so the important point that I want to point out, which sort of maybe is suggestive of the fact that you get a Sierpinski carpet and not one of these other weirder spaces, is that so an important property is if you have Z and Z prime, which are on the boundary of two peripheral subgroups, which are not equal, and if Z prime is in one of these neighborhoods of Z, then in fact the whole boundary of P prime is contained in this neighborhood. Okay, so the weird thing about this picture is that you have sort of this point here where in a neighborhood of it, well, there are some peripheral circles which are not completely contained in that neighborhood. But that doesn't happen with the topology on the Damani boundary. Okay, so this this is not a proof, and it's actually sort of far from a proof, but I think it sort of gives some idea why you might believe this theorem. Okay, other questions? Okay, so the last thing I want to do is tell you how to deduce the main theorem from this theorem. Okay, so this doesn't require much work. I didn't call it theorem A, so it's that theorem. Okay, so G P is torsion-free, relatively hyperbolic. And, well, I'm only going to show one direction, so I'm going to show that if the boundary, the Bowditch boundary is a two-sphere, then G P is a PD3 pair. Okay, so the main thing to show is that, well, the double G delta of G along with itself along the peripheral subgroups is a PD3 group. So let me just remark. So I mentioned, so the way I define PD n pairs is that the peripheral subgroups are PDN minus 1, and then the double is PDN. And in this case, the peripheral subgroups, I already remarked, are surface subgroups, and so they are indeed PD2. Okay, so this is the main thing to show.
Bena, were you
Yes?
torsion-free?
Oh, yeah, right, yeah.
You sort of assumed it in your definition.
Right, yeah, so, yeah, right. If you're working with, so Poincare duality groups are always torsion-free. So that's really what I want to assume. Okay. Okay, so why is the double a PD3 group? So the first input is another result of Damani's combination theorem. Which says that the double itself, relative to the same collection of peripheral subgroups, is relatively hyperbolic. So we can talk about its Damani boundary, and knowing that the Bowditch boundary of G is S2, so by the main theorem, this tells you that the Damani boundary of G with respect to P is a Sierpinski carpet, and it follows that the Damani boundary of the double is a tree of Sierpinski carpets which are glued along peripheral subgroups, or peripheral circles. And what you get is the two-sphere. And so then the fact that, well, this Damani boundary, so now we're done, the Damani boundary of the double is a Z boundary. So this means that, well, the cohomology is the same thing as cohomology of S2, so this tells you that G delta is PD3. Okay, so to close, I just want to state, mention or state an open question. It'd be nice to understand a little bit better what happens in higher dimensions if you have a relatively hyperbolic group whose boundary is an n-sphere. And it'd be nice to prove the wall conjecture in that case. But let me just state a question. Well, so let me just say something concrete. So suppose the Bowditch boundary is S3. So the question is, what are the possible peripheral subgroups? So you know that they're going to be three-manifold groups. They'll act properly, discontinuously, co-compactly on R3. But is it possible to get anything? So in particular, well, so can you get, so I don't know, can you get anything other than virtually nilpotent groups? So remember, these relatively hyperbolic groups are a generalization of negatively curved manifold groups, so finite volume, negatively curved manifolds with cusps. And in that case, you know if you have pinch negative curvature, then the cusp subgroups are always virtually nilpotent. So I don't know if maybe in this more general case, you can get something else. I think that would be interesting to know. And then another question is, do the cusp subgroups always have Z boundaries? Right. So, I mean, I don't think it's known that every three-manifold group has a Z boundary, and even for, well, yeah, I think, so for example, the integer Heisenberg group, I think, does have a Z boundary, but I don't think this is well understood either. Okay, I'll stop there. Thanks.